I'd say on a car like that, the cars with good aero and the cars with bad aero would be separated by a second and a half or 2 seconds by aerodynamically. I mean, if you look at the spread of the field of club sprint class, that's like, I think it'd take you from like fifth or sixth to winning the class.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're chatting to the aptly named Andrew Brilliant from AMB Aero. He's joining us today from Japan. Andrew has been on the scene for a number of years now and is prominent in his design and development of aero packages for all manner of race cars. Particularly, we've seen a lot of Andrew's work when we have travelled to Australia to attend World Time Attack Challenge. And one of the nice things about the rulebook for World Time Attack is that, at least in the top classes, there aren't actually that many rules about what you can and can't do in terms of the aero package. And in the past, we've seen teams essentially try and reduce their lap times by hitting the car with a big sledgehammer in terms of adding a huge amount of power. And granted, that is going to work to an extent. However, with a lot of the pro class cars now at World Time Attack producing power levels in the 800, 900, 1,000 horsepower or above vicinity, there is still a limit to how much power that you can put to the racetrack. Otherwise, ultimately, it just goes up in tire smoke. And that is why over the time we've been attending this particular event, we've seen a massive drive in development on the aero packages that are on these cars. Andrew is probably well known for the aero package that was developed on the Mitsubishi Evo Time Attack car that was known as Nemo. Unfortunately, that one disappeared off the scene, but he is still involved with a number of other vehicles at World Time Attack Challenge. Just two of the cars that Andrew has been involved with include Lyfe Motorsport's R35 GTR. We chatted with Cole, the owner and driver of that car, in a past episode, as well as one of the fan favourites for World Time Attack, which is under Suzuki's S15. Interestingly, as we talk to Andrew about the relevance of aero and how much of a factor it plays into lap times, he shared with us that the aero package he developed for under Suzuki's car back at their home track of Tsukuba, that was worth 3 seconds of lap time. And we're talking about a very short track here with lap times around about the 50-second mark. So you can hopefully understand and appreciate just how much value there is with the development of a proper aero package. Before we get into our chat with Andrew, just an introduction for anyone who maybe has not heard of High Performance Academy before. We are an online training school. We specialize in teaching people how to tune EFI, build quality race engines, how to produce quality and reliable wiring harnesses. We also cover race driver education and race car setup, and we do this with a range of video-based training courses that you can take from the comfort of your living room. If you are interested in learning a little bit more about High Performance Academy's courses, you can head to hpacademy.com/courses. That'll give you a full list of all of the courses we currently offer. And as an added bonus, because you are a podcast listener, you can use the coupon code podcast75. That will give you $75 off the purchase of your very first course from High Performance Academy. Just to mention as well, zero risk with purchase. We offer a 60-day, no questions asked, money-back guarantee with any course purchase. So zero risk, giving them a bit of a test drive. All right, with our introduction out of the way, let's jump into our interview now with Andrew. Okay. All right, welcome to the podcast. Andrew, thanks heaps for joining us today. Obviously, these days you're pretty well known, particularly in World Time Attack realms, for developing the aero packages on some of the fastest open class cars around. But before we get into that and what goes into a competitive aerodynamic package, can you maybe rewind the clock a little bit and give us a bit of a background on how you got involved in motorsport and aerodynamics?
It started with motorsport a long time ago. I mean, it was, a bit of a shed hobby for my friends and I, when we were starting from about first year uni, I would say. And, I started just kind of toying around with my own car. And I always enjoyed motorsport. There was a channel called Speed Channel back home, and I used to just have that on, pretty much 24/7. And they had a, World Rally Championship, FIA GT, all those things. I just would watch that stuff pretty much endlessly. Played with, like a lot of people played with their little toy cars and stuff as a kid, started like that. And then my dad kind of had a bit of a thing for cars as well. That probably contributed. And then when I was in uni, they sort of, I knew for sure that engineering and IT were where I had interests. And, of course, counselors always ask you, when you're trying to figure out what to major in, what do you like? What are you interested in? And I said, well, motorsport. And they said, okay, well, engineering's definitely the right choice for that. So I wound up down the engineering path. And then while I was, then I started getting involved in amateur level motorsport stuff, and then wound up working for this team that, we won the SCCA's. I don't know if you guys have ever heard of it, but it's a really big club racing thing in the States.
Yep.
It's the biggest organization. And then we wound up winning the championship in a bit of a lower class. And then, that's where I really kind of got started with doing aero, because I was just sort of the only person that knew how to operate a computer kind of. And then got a break into pro racing because a team that was doing it sort of caught interest on some of the work I was doing. That was, people saw it on the internet, and wound up getting a job offer to fill in for someone who was out sick at a race. And then it wound up becoming a job. And then I wound up back and forth between Japan and the US doing Super GT and IndyCar at the same time. And then I wound up, the team I worked for, we won Super GT. And then after that, I just really got roped into the Japan aerodynamics work, did some work for Nissan, and then was doing my own thing part-time, and then that just became full-time. And now here we are today with staff and a real business. It just sort of evolved step by step.
Okay. Heaps to go back and unpack in that. What it sounds to me like is a fairly maybe unusual journey down the rabbit hole there. Obviously, engineering, anyone interested in motorsport, it's a pretty invaluable skill set to have. But engineering, at least from my perspective, doesn't necessarily lend itself straight away to in-depth aerodynamic understanding. And to me, again, from the sidelines, aero does always look like a fairly niche topic. So from what you just explained there, it kind of sounds like your aerodynamic understanding and knowledge was, to at least a certain portion, self-taught. Is that right, or have I got the wrong end of that?
Well, so I studied mechanical engineering in university because that's what so nowadays everyone has come to understand how much aerodynamics dominates motorsports. But back when I was in uni, it was like mechanical engineering is the way to go if you want to work in motorsport. It was very much about the mechanical grip side. So I started out in vehicle dynamics actually, but I'd always loved fluids. I was really good with computers. I'd been programming since I was like 8 years old. So it was sort of Actually, let me rewind one step. So I was working as a data engineer, and one of the tasks I got given one year was the team had a car that was developmental. It was, it takes you a few seasons to really become competitive. And the team's got a certain budget with which to develop for the next season, and they wanted to know what was the most lucrative path in terms of cost versus lap time that we could pursue. And I used these lap simulation tools. We did that a lot for things like gearing. For example, you could see how the car would run around on the track, and you could not just optimize the gearing. That was the basic thing you did, but more than that, you could see, okay, well, the computer might want to shift in the middle of a corner. It might think mid-corner you could shift from second to third, for example, but a driver won't do that. A driver will just sort of be stuck near red line in second gear and wait till they've straightened up before they can shift. So we did a lot of simulation to look at getting the right gear ratios and trying to do that before, and using less of our test time for that, having that sort of sorted out, having a bit of suspension sorted out before we go on track. And then we wound up using those simulation tools to evaluate courses for development. So we looked at how much lap time we would get for, let's say, X kilogram force of downforce versus X horsepower gain that we could invest in. So we might talk to the engine builder, and they might say, okay, for this much money, we can give you this much power. So we had to evaluate all those things, and we were making a graph, a coefficient graph. One axis is cost, the other is performance. And you want to just do everything that's in the bottom left corner of that graph, whatever gives you the most lap time for the least money. And it just kept coming back that these little small gains aerodynamically were worth huge lap time. When you start out with light downforce, you'll do 150 or 200 kilogram force of downforce on the car, worth a second a lap, which in GT will take you from mid pack to top three, right? Mm-hmm. So we were like, well, how realistic is it to get that kind of lap time? And then I said, well, we haven't been doing, we did some wind tunnel development, but we hadn't done a lot of CFD stuff. So I said, well, give a CFD a play for about a month and see if we can find that kind of downforce. And I said, all right. So I did a bit of a crash course in CFD, got started. And of course it was quite basic. What we were doing initially, a lot of it was just like optimizing the rear wing a bit, getting it in the right position, all these things that we couldn't do. Is in the wind tunnel, you have to actually make those things, right? If you want to try a wing in 15 different positions, you got to show up with 15 different mounts for the wing, right? So wind tunnel time was very expensive, very limited, and CFD would let us take this sort of sledgehammer approach, and we could change things that we couldn't afford to do in the wind tunnel. And sure enough, I said, I think we can do significantly more than a second a lap with CFD development, because we found a second worth of downforce pretty much right away. And then they just had me just keep going at it, and it just spun out. It just turned into like, whoa, now we're winning a championship,
Again, a bunch of stuff I want to go back and dig into a bit deeper there. So, obviously at the upper echelons of motorsport, the likes of Formula One, IndyCar, etc., obviously it's been no secret that aerodynamic performance is absolutely critical to the performance of the car and winning, and huge budgets are spent on aerodynamics. Do you think at the lower levels of I don't even want to say enthusiast racing, because you look at the likes of World Time Attack, there's big budgets involved in that level of motorsport as well. But do you sort of think more outside of the professional levels of motorsport, aerodynamics has not maybe been seen as such a powerful tool to aid performance as it really is?
I think that's definitely something that's misperceived, and I'll say that because that class that I was working on when I first started doing aero with CFD was extremely limited aerodynamics in terms of the size and scale of what the sort of mid-level GT stuff was allowed back then was 50 to 100 mil of splitter. We had to have an open underbody. By that I mean, for example, in enduro, like FIA WEC classes, for example, it's a flat floor rule, so you can cut off the whole bottom of the floor pan of the car and bond in a flat sheet, to the floor, and that makes you a flat floor. So we had to have the original open underbody in those days and a very small splitter. We had less allowance aerodynamically than Club Sprint class in World Time Attack has. So the idea that an Aero was making the difference between, I'd say on a car like that, the cars with good aero and the cars with bad aero would be separated by a second and a half or 2 seconds by aerodynamically. And that's, I mean, if you look at the spread of the field of club sprint class, that's like, I think it'd take you from like fifth or sixth to winning the class. And yet no one's really developing custom one-off aero there. But my experience from GT is that absolutely it's valuable. And those cars weigh quite similar, that we had a 1,200 kilo minimum weight. So, on spec, I mean, those club sprint cars actually have more power than we had. Some of them maybe even less weight, so I cannot conceive of any reason why it would be any less valuable than it was for us in GT. And the development we were doing was quite basic compared to what we do for like a pro class car. I mean, it was quite inexpensive. I think, we have like our mid-range packages, $8,500. That's 3D scanning and CFD development of a splitter diffuser. I mean, that stuff would make seconds of a difference for club sprint, let alone.
Yeah, I think that's one of the areas I wanted to touch on, and I'd sort of intended to talk a bit more about the costs involved later on, but you've just raised that, and I think there is a perception, particularly, we've spent a lot of time interviewing teams at all the different levels of World Time Attack, as well as obviously events all around the world, and I think in general there is this perception that doing almost anything other than buying an off-the-shelf wing from eBay, etc., basically anything beyond that is just going to cost thousands and thousands of dollars to get the sort of benefit that it potentially can. As you said, your mid-level package, we'll talk a little bit more about what's involved there. $8,500. I mean, people are spending probably that on engine development in a season and not blinking an eye. I think the other thing that kind of comes in as part and parcel of this is, and I've fallen guilty to this coming from a background as an engine builder and a tuner, is that if we want the car to go around the track faster, well, let's hit it with a bigger hammer and just chuck a bunch more power at it, which of course is effective to a point. But then you get to a situation where you're traction limited and you can't put all of the power the engine's producing to the track. At that point, are we then in a situation that with too much power, aero is arguably even more important or more critical?
Yeah, I mean, obviously, the more power you're making, the more you can put it down with aero. I mean, think about it like this: a funny car or a top fuel dragster, that thing doesn't even turn and it's got wings on it, right? That thing goes in a straight line the whole way and they still run wings. So it's obviously got a fairly significant effect on traction. I mean, the amount of downforce that a top fuel makes at those high speeds that they're going is quite extreme. They're going 300 miles an hour, and they're capable of spinning the tires the entire way down the track. So there's obviously shades of that, but we see it. I mean, you see it like, I remember. I'll give you an example. I'll give you a grassroots example, sort of. When I was building my own car, we had a particular problem that it was a front-wheel drive car, and the aero that we did on that car was very lightweight. I mean, we were doing it for what was called the street class back home, so it was about equivalent to like a club sprint class. Did very, very lightweight CFD work, and we wound up probably having similar downforce to a GT car. Well, that car's problem is that once the load transfers off the front tires, you got no traction at all, right? Because it's front-wheel drive. And we would get about 0.55 G of acceleration just with the car as it was. That was the maximum we'd have. After that, you'd transferred too much load to the rear and you had no traction, right? And after we did that lightweight aero, we went to 3/4 of a G of acceleration.
Oh, that's a massive difference.
Yeah. I mean, it was like, I remember driving, because it was still street registered and everything. So I was driving this car around on the road. And after we added that, it was like, it used to be able to spin through fifth. I mean, I could get into it in fifth gear and it would just light the fronts up at highway speed, no problem. After we did the aero, by third gear, it was just dead hooked. And we had 660 foot-pounds of torque and we were dead hooking in third. So, I mean, that was just monster change in the acceleration. And the same is also true for rear-wheel drives. like under Suzuki's car, I remember it was Tarzan Yamato who made a comment. When that car first got tunnels and started having real big downforce, Tarzan Yamato commented to me, he said, I never thought that a rear-wheel drive car would be able to hook and accelerate the way that car does. And the only thing that had changed on the car, and he knew it, was in the last couple of years, had been aero. It had made a smidge more power. It had gotten heavier because of adding the aero with some weight. So, but the lap times had dropped like 3 or 4 seconds, scuba, which is a 50 something second track. So it was, the drivers, even just watching the video, I mean, you just would never dream to put down the kind of power you can with downforce. And the same's true with like LMP cars. When they go to their low downforce trim, all their traction control settings change. Everything like the same thing with F1's a bit different because they've got it so mapped out with the electric assist and stuff. But the amount of power, like the map, they have to change a different map for how power is put down if they trim out the aero. I mean, so even just like a 10% change in the downforce means that a completely different map for how much torque you can put out in the car.
Yeah, I think it's one of those aspects that as someone on the sidelines who maybe hasn't experienced a car with any level of aero, it can be very difficult to get a feel or a sense of exactly what these components can actually do to a car's performance. So it's great to get a little bit of insight from you on that. I just want to talk about the tools for developing aero. And I think a lot of people, again, who are new to aerodynamics would assume that the wind tunnel is the holy grail of developing components and seeing how they react and testing different iterations of these. And definitely back in the earlier days with the F1, before the likes of CFD software was as refined as it is now, that probably was really the only tool they had to rely on. Can you talk to us now about CFD versus a wind tunnel, with the pros and cons of each, and how you go about using the tools available to you?
Sure. Yeah, look, I mean, so, obviously we've got a background in that we've designed and built and installed wind tunnel facilities for Nissan. So we've got, and my partner, Yoshi Suzuka, handles all the wind tunnel development work, and I handle all the CFD side. And the biggest difference between the two disciplines, first of all, is wind tunnel, when done properly, is more accurate than CFD. That's just how it is. It's just, you've got real air flowing over a real model. And there's a lot more things that you can screw up with CFD. For example, the shape of the vortices can be controlled by a setting, right? Where in the wind tunnel, it's just the scale that will affect something like that. That you're using a 50% car instead of a full scale, or maybe the wind tunnel's got some problems that you have to deal with. And that happens a lot. You hear about that in F1. They have a wind tunnel correlation problem. So wind tunnels are certainly not faultless. I would say with the diversity of cars that we've done now, we've come up with really good general settings, and we've been coming out within a few percent of what the cars are measuring with instrumentation typically. But and with wind tunnels in general can be worse. There are wind tunnels that are significantly worse than that, that are even well-known, even renowned wind tunnels that are worse than that. But that's what we call absolute accuracy. And absolute accuracy is not really of that much value, believe it or not. The most important thing is what we call relative accuracy, which is that you don't get a false positive or false negative from a change you make to the car. So changing this shape to that shape tells you that you've gained downforce or reduced drag or whatever that is that you're searching for. And it tells you that you've got it. If that's wrong or a drastically exaggerated or underrated value, that's really the problem. So there's a lot to be learned about how to do CFD, and there's a lot of tricks of the trade of how to do it properly. But the biggest advantage between CFD and wind tunnel is that with wind tunnel, you have to build every change, right? Every change is a physical model that has to be changed. And that requires, if you're doing scale, so for example, F1 will be a 50% scale or 60% scale tunnel, you've got to go and make all those parts and install them on the vehicle and then test it. So that's obviously a huge cost. Like even the base model is, a 60, for example, at a manufacturer in Japan might spend $300,000 to build just a base model of the car. So let's say you want to change a fundamental shape of that car, like a complete change of like the bonnet curvature. Well, that might go through what used to be the heart of your chassis structure inside of the model, not just the change of a carbon fiber shell on it. And in which case you have to make a new model, and you got to take a new model off the tunnel, put it back in, recalibrate everything. There's a huge cost for that. And there's cost in terms of time, days. There's a thing called branch prediction where you've got to say you're testing a wing in different positions. Well, depending on the result, let's say you find a good position or a bad position. What's the next test you're going to do? Maybe the next test you're going to do is changing the diffuser to work better with that wing. So someone's making multiple shapes of diffusers while you're testing the wing. So you're trying to predict what tests are coming next so that the model makers are making all the parts you might possibly need. And you wind up not even using lots of them. So there's a lot of wasted money, a lot of time spent, a lot of model shop work with wind tunnels. So it's quite expensive.
So the difference with the CFD is, if you can imagine it, you can draw a new component out relatively quickly and then run another test with your new virtual wing, for example, as opposed to physically making a real product.
Exactly. So imagine a wing. You can tell your CFD, you can instruct the software to morph things parametrically. You can say, change the camber, change the chord, change the thickness, change the position of elements relative to each other. And, the computer can just stack up generated shapes and just run right through them. So it's sort of I see it as like a sledgehammer versus a chisel. Wind tunnel is very good at being a chisel. It's also very good at sweeping through ride heights and attitudes, because they'll have actuators. They'll have what's called a sting that comes from the roof that holds up the model off of the tunnel floor, and that will have actuators built into it to move the car around to various attitudes. So it's very fast to get the results back for sweeping through attitudes. So like a F1 wind tunnel will be what they call constant motion. It never sits in a position for very long.
So it's mapping the downforce results as it's constantly moving the model through different conditions of ride height and rake attitude.
Right. So that takes a very short amount of time in the wind tunnel, right, to test a different ride height. But in CFD, it's as long as it takes your compute to try different heights, right? So our computer is set up to automatically generate different heights. That helps, but still your computer has to run through those results. So if you've got limited compute resources, like let's say you've got some kind of a high-end desktop computer and maybe it takes you a day to get one result back, well, you can't realistically run through 6 or 7 ride heights on a system like that, right? You're gonna be sort of optimizing it just one.
Sure. Yeah, no, it makes sense. I guess with the CFD as well, I mean, obviously, a lot of the result comes down to the skill of the operator in designing the model and then running the software. I assume it is a case of garbage in, garbage out.
Yeah, I mean, look, I mean, people. I mean, I've seen a lot of people. You can go and spend money. There are people out there, freelancers or places like us, sort of, but they're willing to do this sort of work. Will spit you out one CFD result. Right, so you go and draw something in CAD, and you ask them to give you one CFD result back, and both our designs and those designs will have a pretty picture of CFD and flow streamlines on posted on the internet. But one of those will have been, ours will have done maybe 500 iterations of different shapes to come land on that one picture you see, and those tests have to be guided by an expert who knows what to do with those results. You get a result back and the flow field looks like this, or the numbers are coming out like this. Well, what do you do next? Right. Mm-hmm. And that's a really important question that only experience and skill can answer. So it's just like any other tool. anyone can download the Motec tuning software, right? That doesn't make you a tuner all of a sudden. That it just takes skill, experience, knowledge, training, all those things. We've done 15,000 tests for time attack and CFD as of now, roughly about 15,000, and we've never stopped learning. Never. We get results that blow our mind all the time. Geez, we didn't see that coming. But it's that test feedback loop, just like tuning on a dyno, right? You might think, someone might say, oh, we'll add more timing, it makes more power, well, maybe that's true, maybe not, unless you're getting test feedback and then making a change and iterating. The hypothesis is fairly useless.
Now, one thing that just actually came up as a thought while you're talking there about these iterative sort of test results, and I've got this is obviously well outside my area of expertise, but something that we've seen become pretty popular over the last decade is generative design, where basically a designer can make a part and then give some feedback some parameters into the software in terms of the weight of the part or the forces that it must be able to support, and then leave the computer to basically go through an iteration of developing that part and basically refining it for the design parameters that it's given. Just what you're explaining with CFD almost sounds like it would lend itself to that. Is that something that either A, can be done now, or is maybe on the horizon where the CFD system can actually optimize the aero components itself to suit what you're after, or are we a long way away from that?
I think that both points of view are correct in a sense, saying that it's not that useful and saying that it is. But I believe in that future being the future more and more and more as time progresses, to the point that I've invested a lot of time programming our own artificial intelligence system that uses our library of past tests to do a fair bit of tests automatically. So it's kind of a bit of our trade secret, but more and more over time, the more that that system has been trained by looking at our results, and the more we've learned about how to program it, the more work we're able to let the AI do. But what that's really let us do so far is get the development to a better and better place through the automated system that can just run 24/7 without any interaction from us. And then that's let us take the same budget of time that the customers were paying for and spend that more on inventing new ideas. So what used to, for example, let's say you've got a diffuser and you need to, and it's what we call a convex concave. So there's basically two splines on this curve, and there's a certain number of combinations of the shape that you can have. Well, the AI, or you can use something that's called an adjunct solver. We use that sometimes as well, where you parameterize those different shapes and it just like runs through those shapes. Well, and our AI sort of like learned things, and it looks at how the flow field is on a car and then comes up with what it thinks it should focus on and makes those changes. And the capability of that AI is growing every day, but it has never, and I think it will never, replace that human intuition. And I'll give you an example. We probably learn the most from tests that don't go the way we expected.
Yeah, sure.
So we'll do something and you think that'll gain and it doesn't. And then you wonder why. So you go and analyze it and you learn something new. And, you can only program an AI. It's hard to get an AI to invent new ideas on its own, right? To intuitively invent new ideas. Sometimes it does come up with very interesting things that you learn from, but more than that, I think the AI is still learning from the humans behind it. And maybe someday that will change, but for now, and I think for into the near future, there's the skilled aerodynamicists are still outperforming AI, or certainly at some point you have to hand it off from AI to those experts to take it to the next level.
So essentially, AI, yes, useful to a point, but there's still a reliance on the engineers, the human element, to get the AI somewhere to start, and then maybe interpret and develop from where the AI ends up. That's sort of what I'm hearing from you.
Yeah. So we're probably one of the very few places that are actually using AI generative design for aerodynamics outside of probably F1 circles or really high end stuff. And that's pretty much where I think it plays in is first of all, removing routine tasks. So instead of us generating 20 CAD models for slightly bigger and bigger diffusers, all that basic stuff, it gets out of the way. And then the intuitive side is where we then spend our human efforts.
Okay. Now, when you're faced with a project and a customer comes to you and says, look, we're racing it in this class and we want to see what you can do in terms of improving the performance with aerodynamics. Obviously, there's a wide range in terms of what the rulebook allows. And, we look at, what World Time Attack has been relatively loose, giving the designer a huge amount of room to play and develop, whereas the majority of racing classes are much more sort of restricted in terms of what you can do. My question here is, when you've essentially got a blank sheet of paper and no rulebook, does that make your job easier? Or because there's absolutely complete freedom in every direction, is it actually a little bit more challenging than trying to work within defined rules and limitations?
That's hard for me to answer because it's made it so much more fun that even if it's more difficult, it's more enjoyable because you're getting to invent things instead of you get to invent bigger ideas, right? Instead of being of such a refinement focused thing. If you look at, a good example might be DTM. That's a class where they have a spec underbody, for example. It's all part of the chassis tub, the tunnels, and that's a tunnels really, but you might call it a diffuser. Those are all specified, right? LMP's the same way. And but the top side, they have a lot of freedom, so they're tweaking all these little tiny details, trying to leverage that underbody. So it's a lot of sort of boring routine work, and then you stumble across something that makes a gain. So you're looking at very, very fine gains and accumulating fine gains. So you might do thousands and thousands of iterations to gain 15% on something like that, where with time attack you get a lot more reward for you might do 200 tests and get 30% or 40%. So I guess it's levels of boredom, I suppose you could say. But it's also, when you work on that professional motorsport, it's a lot easier for what you gain in aero to translate directly into on-track performance because the cars are already so optimized and they're run by professional teams and get lots of testing and that. So they're just different disciplines.
Yeah. One of the aspects with aerodynamics and motorsport is, unfortunately, there's no rules around plagiarism. And if we look at the upper echelons, F1, there's been situations where at the start of a season, the cars will come out and there will be some quite different aerodynamic directions that certain teams have gone down. And generally after the first one or two rounds, when everyone sees which direction was the one to go after, two races later, everyone else has done upgrades and basically the cars will look the same again. For you as a designer, would you take that as sort of a frustration if someone takes an idea that you've developed in the off season, it's really unique, it's given you a distinct and noticeable advantage, and then 3 races into the season, every other team's jumped on the bandwagon and copied you? Is that frustrating, or do you take that as a pat on the back that you did good?
I mean, you take it as a pat on the back. I mean, if you look at the time attack cars, for example, the basic pattern of the basic shape of a time attack car, a lot of that stuff we invented with Nemo. For example, instead of let's say a high-low wing, pretty much everyone's landed on a high wing and a low spoiler, combined with tunnels and certain side skirts a certain way and open fenders in a certain way. And I think we sort of pushed the envelope with a lot of that stuff. So I do take a lot of that as a compliment. I mean, things on the top side of the car, obviously everyone's going to see those. There's nothing you can do to stop copying that. But that really only gets you so far, because without the understanding of how it worked with what was underneath the car, and there's still a certain amount of just doing the work. Even though you see that shape, that exact same shape doesn't work on every car. If you even went and took, let's say, molds off of Nemo's body panels, and then you tried to put that onto a different car, it just, you lose these percentages of value.
Is that just because of the way the air sort of flows over the other existing body structures? So how that affects the airflow onto the likes of the rear wing is not going to be the same as it was for Nemo, as your example is?
Yeah, I mean, every car has a different package, right? Every car's packaging is different. So if you try and package the same Aero onto a car that doesn't have the same exact identical packaging, and when I say that, I'm talking about the littlest things, like the position of the dry sump, or the exhaust, or the where the sway bar is. All those things will massively affect what your optimum shape is, let's say, for a front diffuser. And or just your wheel offset, for example. If you change the wheel offset on us halfway through a project, we have to redesign the entire front of the car.
Okay.
So you just can't apply. Well, you can apply generalities if you're willing to accept losing 50 to 80% of your downforce.
I think probably a lot of people would be surprised by that exact statement, thinking that, again, we go to the likes of World Time Attack, you look at the pro field of cars, or any of the classes for that matter, and as you've said, there's generalities that you see across them, and so people would think, oh, I'm just going to basically copy that, and we're going to be there or thereabouts. But what you're saying is that will get you, let's say 20 to 50% of the result, but the other 50 to 80% is how you integrate that with the rest of the package.
Yeah, car specific optimization. I mean, it's hard to understate it, and it's easy to think you've done well, because at the top end of the field, let's say you take a car like under Suzuki or RP968, if you went and took every aero piece off of that car, right? And assuming that you could magically fit the same tires and stuff like that, and put the stock body back on it, you'd probably lose. I mean, you'd lose 8, maybe 10 seconds a lap, right? And I mean, it wouldn't even be in the same ballpark. I mean, the cars at World Time Attack 10 years ago, they had 800 plus wheel horsepower. They had, they're probably a bit heavier than they are now, but the cars are more than 10 seconds a lap faster. And there's too much change in the performance of those cars to attribute it to, 50 or 100 kilo lighter car, or an extra 100 horsepower. Those things don't make a car 10 seconds a lap faster, right?
No, absolutely not. And yeah, I mean, I think it's been pretty clear from anyone with a passing interest in the likes of World Time Attack that the improvements in lap time have definitely come from the aero development, and that's why I really look forward to going every year, because the advancements have been so huge over the time we've been reporting on that event. Now, one of the other aspects that I think is really easy for to get lost or ignore is that it's not just a case of developing a new rear wing, some underbody diffuser, and a front splitter. It's also the relationship between the amount of downforce you're getting on the front axle versus the rear axle, and trying to keep a balance with that as well, so that the car handles well in low speed, medium speed, and high speed corners. So can you talk to us about how that works and what you do around that aspect?
Sure. Yeah, I mean, look, it's actually really quite simple. That what we call COP, center of pressure, needs to roughly follow the COG, the center of gravity, right? So if you've got a car that's got a 50-50 weight distribution, well, your aero shouldn't wind up too far off of a 50-50 distribution. What'll happen is if you run like a dragster type air balance, let's say you had 90% rear, that car will keep a traction out of a really low speed corner maybe, but you get into anything going faster and it just won't turn. It just won't do it. So a lot of, like, for example, getting faster in turn one, I'll tell you the facts and then I'll give you an anecdote. Just going faster in turn one, a lot of that will come down to your aero balance, how you're able to manage how extreme the loads are. You've probably, since the Nemo days, we were probably aerodynamically what we call load saturated, which means the tires already got all the grip it'll give you. Putting more downforce on it won't give you any more grip in turn one because you're going so fast. There's just so much downforce available. Tires just maxed out. And things like getting a car with a better distribution to let you have a more ideal aerodynamic distribution is what was giving us the most gains. For example, in minimum speed in turn one. An anecdote I'll tell you is one of the years that we did updates for MCA Hammerhead, we added the canards on in the race, and we look on the data, and I could tell the car had a bit of a rear heavy balance. And the canards added something like 120 kilogram force to the front, and the top speed in turn one went up by more than 10 kilometers an hour. The minimum speed went up by more than 10 kilometers an hour.
Oh, that's huge.
Which is just massive. And that was just a matter of getting that balance a bit more forward. And you could see that it had so much more in turn one that the driver, Tim, wound up getting a little bit loose in turn two because he I think he may have gotten a sense that there was just so much more grip available. You think that the track's just got more grip in it, and he overcooked it just a bit in turn two. And,
now, for those, we've obviously got people listening to this podcast from all around the world, and we have focused on world time attack through a lot of this conversation. So turn one you're referring to there is turn one at Sydney Motorsport Park or Eastern Creek.
Yeah.
And I mean, it doesn't really matter what track we're talking about or what corner we're talking about, but just to chuck some numbers into the mix, it's a very high speed corner. Can you talk about what sort of speed the likes of MCA Hammerhead that you're talking about there, what sort of speed is the car taking turn one at? What's the minimum speed through that corner?
There's some things I can say, and there's some things I'd have to ask the team to talk about. But I can tell you that in the Nemo days, we had the lap that everyone saw the video for was actually not the car's quickest lap. The quickest lap, it had a minimum speed of 248, that was 2012. I think the fast cars now are doing 250, 260 bottom speeds through there.
Sure,
and a lot of those losses is related to what's called scrub drag, which is just that you've got a lot of weight on those front tires, and they're the ones that are steering, and so they even if you don't lift, you will slow the car down by nature of the fact that you're steering the car. There's just friction involved in that, and so for example, on Indy cars in the oval, you run really rear heavy distributions and to reduce that scrub drag, because you're just wide open at top speed for an entire race, right? If you lift the throttle, the engineers in the driver's ear are asking what happened, So in that kind of a race, it's the same kind of thing. You move it all back to reduce the scrub drag. But so there's a lot to that. But yeah, I think we're around or approaching 260 depending on which team and which car.
Okay, yeah. Anyway, look at the numbers specifically aren't so important around just more the generalities of what we're talking about there. Now, in terms of the center of pressure, does that change with, obviously the higher the speed, the more downforce in total is going to be produced, but does that center of pressure tend to move depending on whether we're going through a corner at maybe 60 miles an hour versus maybe 150 mile an hour?
Yes, and I'll tell you why is probably not what some people tend to think, that the aerodynamics is changing with speed, that the speed of the air is what matters. For all intents and purposes, for a racing car, that is a mild concern at best, because there's this thing called the Reynolds number. It's a complicated formula for the behavior of air and its relationship of the viscosity of the air versus the scale and the speed. But basically for a race car, by the time you've got enough downforce for it to matter, you're moving pretty quickly, right? So let's say you're moving 60 or 80 kilometers an hour before you start to really have a quite significant effect from the downforce. And then, at the high speed, you're not doing like an airplane. You're not doing 600 and something miles an hour. You're not doing Mach 0.9. So for all intents and purposes, we consider the Reynolds number to be fairly linear in the speed range that a racing car operates in. That may be different for like a Top Fuel or maybe even F1, where they'll be doing 340 or for extended periods. But I mean, for cars like this, you just don't worry. We don't worry about speed related things. But the biggest thing that changes is with ride height, it changes massively. So the air balance migrates a lot with ride height. And that's going to change with speed because the aero load is changing so drastically. You've got cars that are making, let's say, 3 times their weight in downforce. What height that car is going to be sitting at when you're pegged into turn 1 at Sydney Motorsport Park is a very different number than when you're when you're at the paddock at speed 0, right?
Yeah. I'm glad you raised that, because that's another topic that I wanted to segue into. So this is as good a time as any. And again, I think this is something that's very easy to overlook, the effect of that massive amount of downforce that it produces at, let's say, 270 kilometers an hour versus stationary in the pit. So the effect of that, of course, is to compress the suspension. And as you've mentioned, the aero downforce is very dependent on the ride height. So the ride height in the pit lane, much different to 270 kilometers an hour. So we've got that effect. But the other thing is just physically the suspension design and what we need to factor in there to keep the car from bottoming with so much downforce. There's a couple of ways we can deal with that. One is to fit massively stiff springs, which kind of is a fix for the high speed problem, but the downside is that's going to potentially affect the mechanical grip at low speed where we don't have that downforce. So that's a compromise. Then we've got the potential to use the likes of bump stops and packers to purposely run down onto the bump stops at high speed and use those to aid us. Or alternatively, in higher levels of motorsport, there's the option to run a third element, a separate spring and damper, which works when the car's being compressed equally on both sides. So can you give us a little insight into, obviously I've just mentioned a bunch of stuff there, can you give us a bit of insight into those topics and how important those are, and how you need to work with a team when you're developing the aero side of things, but also that needs to be factored into the suspension development?
Sure, yeah. I mean, it's... God, there's a lot to talk about on that topic. I came from vehicle dynamics, and then went to aero, so that's sort of my original background. But I got to think of a real concise way to put this. But I think you've pretty much summed up the basic problem, right? Which is that, the real question I guess you'd start with is why is a softer car faster mechanically, right? Mm-hmm. And that's pretty straightforward. It's just that. The tire is this viscoelastic thing. It's and if you've ever played with a viscoelastic substance, if you hit it with a hammer, it might not penetrate, but if you reach in through it slowly, it your hand can go right through it, right? And tires, when you shock them, they react and you lose grip. I mean, it's as simple as you can put it. So the harder you are on the tires, the less grip you're going to get out of them. So when you need mechanical grip, you want a car that's really soft as you can possibly go. And then when you want to deal with aero, you want a car that's as stiff as you can possibly go. So everyone tries to deal with that with various methods of progressive springing, right? Bump stops, packers, as you mentioned, that's an easy way to do it if you have 4 corner springs. But in terms of a lot of aero-dependent classes, when it's allowed, almost certainly they will use a heave spring or third spring or whatever you want to call it. Yeah. And the easiest way I explain that to people is, it's the exact opposite of a sway bar. The way a sway bar works is if you roll, one corner is compressing, one side of the car is compressing, the other one's extending, and there's a spring, a torsion spring connecting the two sides together. So the other side will react in some degree to the compression load on the other side. So if you're turning left, your right side wants to compress as the car rolls. But the left will also get picked up. The inside will also get picked up by the sway bar. And this is the exact opposite of that, where both sides can move freely, but when they move together, so then it engages the third spring. So it'd be like if you had a separate shock and damper in the middle of the sway bar, so that if both sides move together, you engage that spring. And that's a huge advantage for cars with this much downforce, because you wind up with, let's say, a progressive spring stack on the third. Well, firstly, it's a lot easy. You don't have to, with corners only, let's say, with 4 springs on it, you have to damp for the expectation of the high spring rate. Otherwise, the car will bounce violently. And you've probably seen that on some cars in the years past, in time attack, where they were struggling with getting that right. You didn't want to put the damping in that you need for the low ride height, but because it'll just destroy your grip in the slow stuff. So there's a lot of tricks you can do with damping, but if you put it onto a separate heave spring, then you are only dealing with that damping problem for the heave mode, not for your roll, not for your you get a lot of freedom, for example, to run over a curb.
So it decouples the aero side of things from the normal operation of the suspension.
Exactly. You've decoupled heave mode from roll. It also, by nature of having thirds, because you're controlling that heave mode on each axle, you also significantly reduce the pitch of the car. Which means that you have to worry less about, for example, the splitter bottoming under braking, because the car wants to pitch less than it used to. So it lets you get a better compromise in terms of the softness of the car in the low speed things. And I think for time attack, that's especially important, because if you look at a Formula One car, that's a car that, let's say, without any aerodynamics on it, would corner at 2.5 Gs, right? So their corner speed is so much higher by nature of the car being lighter and having a lower COG and all these other factors, that they are in aero all the time. They're always engaging. They're fast enough to engage the aero all the time, right? And a time attack car, you'll have a mid-speed corner where you're seriously using aero, and then you'll have a low-speed corner where your aero load will be quite small, maybe just a few hundred kilograms. And in that case, you really want that car to work mechanically. So we have it tougher, I think, than even a Formula car, because while they do this to the nth degree and to the little tiny minute changes, we really have to consider a much broader operating spectrum. So we really try to, we reached what we call peak downforce, which was when we felt that the cars weren't getting faster from more downforce. We got that about 2016. And every year since then, we've concentrated almost completely on broadening the aero map so that you've got more downforce at high ride heights as well as low, making the car easy to drive, easy to set up, reducing the drag, so getting a better lift to drag ratio. I mean, we've focused almost entirely on that since 2016.
Yeah, I think that's probably something that, again, from a layman looking on from the outside, you wouldn't have necessarily picked that. You already peaked at the maximum downforce levels that were useful. Again, you've mentioned about a dozen things that I'd like to dig into there. We've talked a little bit with those third elements, third springs, heave springs, whatever you want to refer to them as. And for those who aren't aware of obviously without the aid of some pictures here, it's difficult in a podcast to really explain that. But essentially, if you have a look at some photos on the internet of the front and rear suspension of any Formula One car, LMP1, LMP2 car, they all run this third spring system for that purpose. So you can sort of get a sense of what we've been talking about by having a look at that. Now, just the sensitivity of the ride height of the car to the amount of downforce that's being produced, or the relationship of downforce to drag. I mean, I know with Formula One, they go to extremes there to try and optimize and keep that car working in a very, very narrow range of ride height. There was the era where they went through active suspension, which was obviously an absolute godsend in controlling that ride height absolutely perfectly. But then back to passive suspension, various teams went through, I think they called it front-rear interconnected suspension, where they basically as the rear of the car dropped down with the aero downforce, it actually raised the front up. So that it kept the front of the car off the ground. Long story short, they're allowing the static ride height when the car was stationary to be lower without the thing being driven into the ground at high speed. So, I mean, if we double that back from the pinnacle of F1, do we see the same sensitivity to the ride height in terms of downforce and drag on the World Time Attack cars that you're developing as well, or is it not quite to that extreme?
There's a sensitivity in terms of what the downforce, how much the downforce is changing, right? And then there's as a numerical value of downforce. So we call that, when we aero map cars, we call that sensitivity. But there's also sensitivity in terms of the lap time output of that change. For an F1 car, the sensitivity in terms of the change in lap time is on a completely different scale than what we see on a time attack car. So you might get the same kind of a change in lap time on a Formula One car from 30 kilogram more downforce that we get from 200 kilogram force change in a time attack car. So they're extremely sensitive when you think about it in terms of lap time. So for them, they just basically would want that car locked at the at minimum ride height all the way around the track. But what they're fighting against is a regulation for plank wear. And the plank wants to wear inevitably at its front tip. And there are a lot of very, very small amount of wear. I can't remember what the rule is now, but some years ago, it was like 1 millimeter of allowed wear in the plank, so that you just can't have that thing touching the ground. So they went through so much of that FRIC. What you're really doing is you're designing the car to rotate as it loads up under aero. You're rotating it around the plank, and because the plank is behind the rear axle, where that front tip of that plank is, then you wind up with a front ride height coming up and a rear ride height going down as you go up. And when the car is flat like that, it has lower drag. All those things. The other thing you can do is you've got an aero map, and you can carve your way right through this. The aero map looks just like a tuning map. Where you for example, a fuel map where it's a 3D graph, for example. I know people do it with VE now, but let's say you got a graph where you got like RPM and injector duty cycle is your Z-axis, and RPM and low and map pressure for that, right? Same thing. So what it'll be like front ride height and rear ride height. But now that you can program a specific line right through that map that it does, well, now you can just give up on whole regions of that map. You don't care about them. You can optimize the car for this exact line that you decided to draw through that aero map. And that lets you, so like what I was saying, when we put all this effort into broadening the aero map to make the car work at, let's say the car 50 millimeter static ride height, let's say, is a regulation for a lot of time attack things. And then you might optimize for like 45 millimeter for the slow speed stuff, and then the fast stuff you're looking at 25 or even 20. And if you've only got to worry about 25 millimeter, and you don't even need to test any of these other things, you just go all in for peak performance in that one specific ride height. You can make huge gains when you don't have to deal with motion of the car. I mean, it's a completely different beast, right?
Sure, yeah.
So does that answer your question?
Yeah, I think that gives us some insight. I mean, obviously, it's difficult here to relate what they do with the likes of Formula One to what is done at even the likes of World Time Attack. But I think it's safe to say that Formula One is, a lot of our listeners watch Formula One, so there is an understanding at some level of what goes on, and it's interesting to sort of see how that relates to the likes of what you're doing, because it's still essentially dealing with the same elements, just at a different level, correct?
Yeah. I mean, their stuff will be, first of all, their minimum ride height is very low compared to ours, so their the ranges that they're working in are really, really narrow. Their stuff is, how peaky. So we have an F1 customer, and so we run them through the exact same CFD processes that we run time attack cars through. So I think we can fairly reliably say that they are extremely sensitive in comparison. That that's all changing a bit this next year, that they're allowing tunnels. I think that will significantly decrease the sensitivities. But anything with a flat floor are very sensitive, and that's why in the early days of flat floors they had those blowovers. People doing backflips and stuff. They didn't have full motion in the wind tunnels, and the sensitivities were so bad that the squat that the car would pick up, because it had a rear heavy aero balance, right? A mid-engine car, so it's rear heavy, so they've got a rear heavy aero balance. And that little change in the pitch that they would see down the straightaway would cause the car to have more lift in the front than it had weight in the front. And next thing you know, the thing's doing backflips. So, those sensitivities can be really, really nasty stuff. I mean, like life endangering. It's a really important, really critical thing to get right. And so we work really hard on that. I mean, our computer generate every day. Our best runs from the day get generated overnight to run in through the whole array of attitudes.
Sure. Yeah, I mean, no one really wants to see cars becoming airborne, and that obviously it's not going to take a rocket scientist to figure out that could end pretty badly for both the car and the driver. So, yeah, can't understate the importance of getting all of this correct. You just mentioned the changes for the aero rules for 2022 for Formula One and the reintroduction of tunnels. And this is something that we are hearing in a lot of racing classes, and I think it's one of the reasons Formula One has gone down this path is to reduce, I think the term that we not normally hear is aero wash. So that's the effect of the flow off a car on a car trailing that. And it's not just Formula One. Locally here in New Zealand and over in Australia, the probably the pinnacle of saloon car racing is the V8 Supercars series, and those are aerodynamically on face value pretty basic looking packages, but they still have had problems over the last few years where the cars can't follow each other closely through corners because the aero wash coming off the leading car basically destroys the downforce on the front splitter of the trailing car. Then the car can't turn because it understeers. So that's obviously a big problem. We want to see close racing where the cars can follow each other, and that obviously in turn produces passing opportunities. So getting away from this issue with aero wash is pretty important to make for exciting racing. From an aerodynamic standpoint, what can be done to clean up this aero wash and make that less of a factor?
Yeah, I mean, I think, well, we've seen F1 trying all sorts of things, right? They've been working at this problem for more than a decade now. The first attempt was when they went to narrower wings and all those things. So, part of the problem is that, some of these cars, so with a Formula One car, the tires are exposed, and those are really blunt devices. They leave a really nasty wash on their own, which is basically unavoidable. A V8 supercar is a relatively blunt object as well. It's got a pretty dirty wake. They're not nearly as streamlined as like an LMP car, for example. So yeah, I mean, there are different. It really that you can design devices to work in dirty air, right? But you don't, because then all of a sudden you get in front and your air doesn't work anymore. You can't design for both. That's a problem. And obviously anything that's a dirty air device will make less downforce than a clean air device. But that's the other problem. And then, for example, the rear wing gets a lot dirtier air because it's behind the car. So that'll be a bit more of a dirty air device. So that might be a lot less affected than a front wing, for example. So you wind up with a bad aero balance. And then, like we were talking about earlier, the car just won't turn in the fast stuff and you just fall behind that car ahead of you. So no, it's a real problem. I think that they're making major strides to do that. I honestly never understood why tunnels were ever done away with in the first place. Everything about them was better. They were less sensitive. They were safer. They were had less wake, for their dirty air problem. So I was really happy that they made the decision to go back to tunnels. I think that's a huge step in the right direction. And if we ever get the liberty to design a car with choosing what aero it would have, we would always do tunnels. Absolutely. I mean, tunnels are basically a no drag, high downforce device. No drag even sometimes can reduce drag with tunnels compared to.
Okay. Yeah, I think that would be probably counterintuitive. So compared to the visible stuff above the body line, the tunnels, huge free kick in terms of lift to drag.
Yeah, it's a huge game in terms of L over D. I mean, anytime you pick up a heap of downforce with no drag, I mean, your L over D is going to just skyrocket, right?
So are there downsides to it?
I have not found a single downside to tunnels other than pragmatic issues. For example, there is no implementation of tunnels that uses a road car's factory rear suspension, for example. It's just, I mean, no road car has long rear control arms for, I mean, maybe there's a few in the world, but pretty much every platform out there has a control arm that's probably.
So it becomes a packaging issue for the modified cars that we tend to see.
Yeah, it's a big construction project, right? You got to cut out the back of the car, you got to redesign the rear suspension, you got to support it from above via the cage. For a lot of teams, we find that level of construction is a bit out of reach. So then that's kind of the people we tend we will recommend them to go with a less expensive aero package, because, if they can't build what you've designed, of what value was it to them, right? So you have to choose your budget, kind of going back to the wind tunnel thing with time attack. I believe this is especially true, that over quality is a bigger problem than under quality. So if you went and recommended a time attack team that's got very limited construction resources to use wind tunnel testing, for example, they'll spend their entire budget on like 4 wind tunnel tests, and then you're fine tuning devices that are going to be thin and small and really high accuracy to produce, but the guy making it is hand sanding it in a shed. He can't even produce to the accuracy you're designing to. So we wouldn't put tunnels on a car with very limited construction budget. We would focus on, specific components, front diffuser, side skirts, probably try to use off the shelf components as much as possible for the top side and be optimized for them to reduce that construction budget. So it's really important that you fit that, whatever you're designing, whatever you're designing it yourself or building it yourself. The biggest thing you have to ask yourself is, what can you realistically build? What are the people who are building the car good at? So that's why we'll never design 2 cars the same. We do 2 Lancer Evo 9s in a row, and they'll come out absolutely different in almost every way.
So just really looking at what the strengths and weaknesses of your particular customer are for that project, and then basing your decisions around something that's workable for that team.
Think about how different your design might be in terms of drag. If one customer's got 900 horsepower and the other one's got 550, that's a completely different car, right?
Yeah.
Or like I said earlier, like the wheel, they've got a different offset of wheel. Well, all of a sudden that's a different fender, which means the diffuser, the front diffusers are all in different positions. What width and contour the front wing wants to be will change, and all this, it all adds up. And the front fender, if the front fender is wider, it affects the shape of the diffuser, because the wash from that's going into the wing, and some of it goes under the car. Everything changes.
Yeah, huge number of knock-on considerations. I just want to come back and see, maybe you can actually give me a solid answer on this. I talked about pros and cons of the tunnels, and I can't even tell you where I heard this, and there may be some truth to it, or it could be urban myth that I've heard and taken as gospel. And I think this came from the earlier days in F1, where they ran underbody tunnels. And back in the earlier days, I mean, those were even sealed to the track with sort of movable little side skirts. And the story that I heard was that they produced a huge amount of downforce, but the problem or the danger came in that if the car got a little bit sideways, basically the flow through those tunnels would then stall, and they went from producing massive amounts of downforce to no downforce, and the car would basically fly off the track.
Sure.
I don't know. Is there any truth in that? It sounded somewhat plausible, but again, I'm not an aerodynamicist.
All right. So what you're talking about, it's called yaw sensitivity. And I mentioned that there was a thing we call a blowover. That's when the car actually picks up off the ground. So there's a yaw blowover. That's fairly common. That's actually more common in modern aerodynamics than, so the old ones that happened back in the 90s when they first went to flat floors, those are pitch blowovers. So where the car pitches up and it gets lift in the front and did a backflip, right? Yep. A yaw blowover would be, for example, about, I think 7 or 8 years ago, the Toyota LMP car got sideways and then had a blowover, picked up off the ground and flipped. There was an incident just a few years back where a GTR GT car had a yaw blowover at the Nürburgring. Although the car was going straight, it was a crosswind that picked it up. And that's actually a problem with road cars too. So Japan went to a near zero lift, we call NZL, is a legal requirement for cars designed here, because there was an incident, I think 30 years ago, where a car came out of a tunnel into a huge crosswind, and it actually picked the car up, flipped it over the traffic on a traffic jam on the other side of the road, and went down the side of a cliff and killed a family. That was a road car speeds,
Wow.
So that's called a yaw blowover. And that, so even if it doesn't blow over, even if you just get a huge amount of lift, well, you're going to get a massive change in your aero balance. All of a sudden you might have like a 70% front aero balance on a car that's 60% rear. The F1 back in those days was like 65-ish rear. So a car like that will just be undrivable, right? It's tend to spin. I don't know how you drive a car with that kind of aero balance. So those kind of sensitivities were a big deal, but they weren't equipped in those days to test those sensitivities. When the wind tunnel models were fixed in the tunnel, they were in exactly one position, and you'd choose the ride height and you'd optimize for it. So they couldn't even see that. And then doing yaw in a wind tunnel is actually quite difficult, because you have rolling tires on a rolling road, and then you're trying to rotate this model, So it's that's a lot easier done in CFD than in the wind tunnel. You need a very expensive, very high-end wind tunnel like F1 teams obviously have to do yaw testing. But that's a really big deal. But it's certainly solvable, because now aerodynamicists have the tools to look at those things, and we do look at those things. We look at yaw sensitivity of devices. So like our Infinity Wing, for example, is a device that actually gains in yaw. So we try to design the rear wing so that it performs similarly or improves its downforce with yaw. So you try and make the car, even if you lose or gain downforce, the most important thing is that it remains stable with yaw. Typically when you're driving in a corner, you're in yaw all the time. If you're cornering, you're in yaw. And so there's a range of yaw that you must design for, and then there's a range of yaw that you just need to keep it safe. If the car spins, it won't pick up off the ground. But you're not worried about aero balance and perfect handling when the car is 90 degrees sideways. You just want to keep it safe, keep the car on the ground, and hope that it just spins and then recovers, right?
Yeah. All right. So it sounds like probably there was some truth to that that story I'd heard, and it sounds like maybe back in those days the technology and the understanding just wasn't as good as it is now, and you guys with the modern CFD can account for that and basically engineer that sensitivity out of it to a degree.
Yeah, I mean you firstly design for it to be safe, and then you actually look at how you can gain performance in yaw. So we actually, all your cornering will be done, let's say a few degrees of yaw, 3 to 5, depending on a lot of factors of yaw. And so you might actually design your aero optimized for downforce in yaw, and then you want it to have when it's going straight, you might actually want it to have less downforce and less drag, right? So each of those questions matter when you firstly characterize the car and talk a bit with the team and understand what ranges the car needs to operate in, and then you define how you're going to run your project to make sure that it as high performance and optimized and absolutely safe in its running conditions.
We are starting to go a little bit long here, and as with most of my interviews. I could probably speak for another hour on this. There's been so much interesting stuff that you've brought up that I'd like to dive deeper into, but we do want to respect your time here, Andrew. One question I do want to just ask before we sort of start wrapping this thing up. We've talked about the CFD, we've talked about wind tunnel testing. When it comes to actually track validation to see how your design is performing out in the real world on the racetrack, what sensors and inputs are you relying on? What sort of data do you want to see?
Yeah, sure. So we really push our customers to do validation, not only because it's a huge value for us that we're constantly validating our CFD because every time we validate, we can improve our accuracy, right? And then there's always, and every car is different, so there's all these different scenarios. We get a broader range of scenarios that we've correlated. But more importantly than that is that a lot of the times things don't come out quite. The computers inside the computer is an imaginary fantasy land. You can draw any shape you want. How that actually comes together in the real world, things also bend in the real world when they're loaded, and you can come up with a situation where what you've expected in CFD is not happening in the real world, and you need to understand that every time. You need to understand, firstly, you got to rule out did anything go wrong with the CFD, which that's actually been quite rare. But more than that, it's usually something isn't quite right with how it got put together. So there's a lot of misunderstandings that are possible. People read a CAD drawing a different way, or something gets put on and then taken off and put back on by someone that didn't understand how it was supposed to be. And then, these little things will add up and make a big difference. So we had one customer who we scanned the engine without the dry sump on it. And they went to put the car together, and the dry sump was hanging out into the front diffuser, blocking off half of one side of the diffuser. So, and then they'll come back and say the downforce isn't right. And you go and look at the car, and you'll be like, okay, well, that's obviously a problem. We've got to change the bracket for the dry sump. That was a good example. But so yes, you absolutely must correlate. The most basic way to do it, and I always recommend this, at least for entry level, is to use shock potentiometers, because that's also very useful for your vehicle dynamics work. And going back to when you talked about springs and bump stops and all that, you can use it to know when you're engaging bump stops, where your bump stops should be. All those things you can optimize using shock pots. The biggest thing is the shock pots is a lot less accurate in terms of measuring the load, because there are a lot of factors affecting the stroke position, including damping, including bump stop engagement, which is a bit of a fuzzy thing. So, when we do shock pots, we tell our customers to do what's called pylon testing. And pylon testing is literally everyone piles on the car while it's on the scales, and you map out the loads versus load on the scale versus shock positions. You can sometimes with the higher downforce cars, you just can't get enough load on the car to correlate the higher end of the loads. So one of our customers, for example, built a thing that went across the strut towers and had a post up to the roof, and used a bottle jack to load up the front of the car to get to those points. So shock pots.
So is this just allowing you to kind of build up a correlation between a measured amount of load on the car and what that actually shows in terms of a shock pot movement?
Correct. Yes. You need to do that. You really must do that, because there's so much going on that the spring displacement doesn't exactly add up to the load. There's what we call installation stiffness. The stiffer the springs get, the more and more of this you'll see. That what the spring is actually mounted to is moving. The chassis itself is bending. And when you've got really stiff springs, a millimeter or two difference in the displacement can be a pretty significant force value. So it's really important that you get a lot of non-linearities as well. With that, you get like at this stroke, the spring rate might be accurate, but at some other stroke, it gets way off. So we've had customers where their correlation was horrible, and then we just kept insisting they do a pylon test, and then all of a sudden it was spot on. So strain gauges are an easier way to do that, though getting strain gauge instrumentation is a bit more difficult to do. You're either strain gauging a shock tower or maybe a strain gauge spring mount, or the bottom of the shock, for example. If you've got a coilover damper situation, it's a bit tough with struts. But yeah, there's a lot of different ways you can do it. Strain gauges, for measuring downforce, strain gauges is ideal. You probably want a pitot tube as well, so that you're getting a corrected airspeed, because you can have a headwind down the straightaway, or a side wind, or a change in the air density that will make your aero numbers go funky. And if you're using a pitot tube for a dynamic airspeed, you're always correcting for those factors.
So it's more than just the ground speed that we actually need to take into account, which obviously that's what we're most used to considering when it comes to a race car, but it's the pitot tube's really a key tool.
It is, yeah. I mean, you correct for temperature as well automatically with the dynamic pressure. So sometimes we went and did testing out in the desert, like on the dry lakes testing or on proving ground testing, and some of those places it'll be freezing temperature at night, and then it'll be 27 degrees in the day, or 30 something degrees in the day in winter. And that the difference in air density between 0 and 30 is huge, So yeah. all your air numbers will walk around. And then, so did that change cause you to lose downforce, or is it because it took you 2 hours to install it and the temperature went up?
Yeah, that's one of the challenges with making back-to-back changes. Is it's also important that nothing else changes when you do your two tests. And yeah, as you're mentioning there's such a host of things that can vary between just a few hours that trying to keep a consistent benchmark for your testing can be really, really challenging. Look, Andrew, I think we'll move towards wrapping this up now. As I've said, could spend another hour with you, but we won't. There's a few questions we like to ask all of our guests, and the first of those is, what's next for you in the future? We're just sort of hopefully on the end, we hope, of COVID, and the world can start getting back towards some travelling again. I know you said before we started this interview that a lack of travel has been difficult for you. So yeah, what's coming up in the future for you?
Yeah, I mean, fortunately, one of our more recent developments is we started doing a lot more work with prototypes and Formula One. So those require a lot less travel because the teams always have their own scanning capabilities and engineering capabilities in-house, which has made being on site a lot less important. But a big part of why I like to go on site too was just to train teams up about their understanding of aero, and teams like that, they're already pretty up on it all. So there's a lot less value in being there. But yeah, I mean, I see us shifting. We've been shifting more towards. I started out in pro motorsport and then spent a lot in time attack, but it's pendulum's kind of swaying back the other way now. So we've been doing more LMP and Formula stuff. We've grown our compute significantly. We actually have more compute than our Formula One team customer does. So, wow. So we're actually able to solve faster than ever. We can break the rules, right? They've got rules, but it's a bit tricky what we can develop for F1 because of their regulations. But anyway, so I see a bit more of that work happening. I see that there's a lot of change in our industry, let's call the aerodynamics development industry. There's a lot more interest in transport efficiency into the future, because that's just become such a huge thing globally. And there's a big push now for countries to go green, having zero, like for example, Japan is setting like a hard deadline for zero emissions for the transport industry. So there's a huge push here domestically to improve the efficiency of anything surrounding transport industry. So I think that's where I see the future moving.
Yeah, definitely. Efficiency is becoming more and more important. So yeah, that obviously makes a lot of sense. In terms of your involvement in more levels of professional motorsport, that's got to be exciting. Obviously, being involved at that level you sort of I assume, get to see the cutting edge, even if you are maybe a lot more restricted in terms of the rule book you have to play by. But I can only imagine that a lot of that ends up feeding back into your more open rule books like World Time Attack anyway. Next question I've got for you is, given your relatively extensive career so far and everything you've learned, if you were to give any advice to a younger version of yourself, maybe to fast track that career progress, what would that be?
Well, I mean, I guess it's a bit of a personal thing, but I think I would have told myself to stick to my guns a bit more about some things. There were times that I knew that where a customer wanted to go was going to lead us into trouble, and I would just sort of accommodate their requests, and then we'd find ourselves in trouble. There was definitely a few times I felt like I should have stuck to my guns a bit better. I grew up in this world where there was a lot less spec aero. Everyone was developing their own aero. Every team developed their own aero. So we were all very secretive about the aero, and it was, the source of lawsuits. The guys that were making components would all of a sudden another team they make components for would stumble on the same design, or, things like that. So it was all very, very secretive. And I think, one thing I learned was that there's just an endless stream of people who will do that, who are going to try and copy your innovations. And, I even went as far as someone had lied to us to get us to disclose under NDA a bunch of designs, and then went and basically bad copies of it, bad replications of it, and marketed themselves using it. They launched a whole business based on it. And, we dealt with that with legal stuff, and that was really expensive and turned out to be a bit of a waste, frankly. But, I think probably I would learn from that too. And I think focus more on branding that you've invented the idea than trying to protect it. Because it's just impossible really to protect it indefinitely.
I think that all makes sense, and I've seen elements of that across my own career as well. I've seen components and ideas from my last business that were knocked off by other companies and marketed. And at the time, that gets quite frustrating. But I think there's not a lot of good that can come on focusing too much of your energy on that. You can't change it. Generally, lawsuits, the only people who win out of that are the lawyers. Yeah. And really, I think you're best just to take it as it is, and then focus on the future developments, because the people that are copying you, the thing you have to keep in mind is that they're always going to be one step behind, because they don't know what you're developing next. And I think if you keep that mentality, it's pretty good advice to live by, in my opinion.
Yeah, I think so too. And I think how upset about it I was at the beginning, to the point we forced them to pay a settlement. Of course, you got to subtract the lawyer fees out of what you get. But looking back on it, I see the work that they've done then. Even with that shortcut, they never really understood why or how the technology worked. And so what I see what they're able to actually achieve, even though they've gotten this potential shortcut by stealing the technology, I see them making so many mistakes surrounding it, in the implementation, in the details of the design, or when they try to reapply the same design to another car, I see them making major mistakes with it. And all that stuff adds up. And I've come to realize that they're never going to get close to the, every time you make a copy of something, it degrades, you make a copy of a copy of a copy. And it's like that telephone game, by the time you get to the other side, that's a completely different word than you started with. Right. And, it's the same thing, I've come to realize that they just, if you are a copycat, you will never perform the same. It's just how it is,
Yeah, and I think the other thing is most mainstream customers probably know the companies or the people out there who are just copying other people's designs. All right, last question for today, Andrew. If our followers want to reach out, follow you, find out more about what you're doing, or As you mentioned, you actually offer some surprisingly cost-effective options for those who want to get a better understanding of their own aero and start producing their own components. How can they reach out and get in touch?
Yeah, sure. Actually, anyone out there, feel free to email me directly. It's just andrew@amb-aero.com. That's also our website address, amb-aero.com. There's a feedback form on there, an inquiry request form that you can fill out, or you can just drop me an email anytime.
Perfect, and we'll drop that into our show notes as well. All right, look, thanks heaps for your time today, Andrew. Really interesting discussion there on aero, and hopefully we will get to see in the not just too distant future your continued efforts with the likes of World Time Attack, and maybe by the sounds of it, Formula One as well. Great to chat.
Thanks, mate.
All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpaacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpaacademy.com/courses.